long identity, right? And there's a lot going on. There's lots of different identity steps, even more algebraic steps. And to me, this is one of the harder identities I'm going to ask you to prove. I now need you to try one similar to this. So have your notes open to this exact example, and you're going to work through a similar example to verify. Okay, so look at the steps we did, work to get a common denominator, go from there. Yeah. Oh, yeah. I have all the identities as well. So similar steps. I condensed some of these steps down though and did a couple things at once, but I'd say this is an appropriate amount of work for this particular identity. So let's just real quickly sum up what I did here. So the first thing is just working to get the common denominator. So first fraction by sine over x over sine of x, second fraction by 1 over cosine of x. Then there's a lot of distributing and FOILing that we need to do. Okay, at least in the first one, it's just sine of x times sine of x. This time around, I did leave the denominator in that factored form. That's probably a better idea because we know that we want some things to divide out as we work through these. And when I leave it in this factored form, then I don't need to distribute and then refactor at a later time. Okay, I have in the back of my mind that I might need to distribute that sine of x in this denominator at some point, but if that comes up, that'll be at a later time. On the right side here, this is the result of me FOILing 1 plus cosine of x times another 1 plus cosine of x. I already combined my like terms of the cosine of x's, which is why it's 2 cosine of x. Then I add the fractions together, rearranging sine squared and cosine squared to be next to each other, just so that it's really easy for us to pick up on the fact that that just equals 1. So 1 plus 1 is 2, and then we get 2 plus 2 cosine of x, and that 2 can then be factored out. And then the 1 plus cosine of x is divided out, leaving us with 2 over sine of x, which is 2 cosecant of x. Okay. That one's hard. Okay. And that, like I said, I would picture that one to be more of an advanced level. There's lots of algebra involved there. Not really a ton of identities that we really used, right? I think the only identity step that we did is this Pythagorean identity, calling it 1. Other than that, it's all algebra. All right, questions there before we move on to our next one? Go ahead. What's your question, Peter? Into your notes, and then after we're done with this, you're going to do the next problem on your worksheet. Ellie, put the phone away, please. Okay, now, I've been saying, and I really emphasized yesterday, that when we're solving or working to verify these identities, we just work with one side of the expression, which that's what I want us to do for the most part. However, with this one, we could actually verify it pretty easily by cross-multiplying. And the only reason I say that is because if we don't recognize a really important thing of what this denominator is and how we can kind of change that denominator to eventually get sine of x, it's a really hard one to pick up on. Okay, so here's the kind of formal way of doing it, and then I'm going to show us the way that we'll take a shortcut. So the formal method here is to recognize that our denominator, 1 plus cosine of x, has a conjugate pair that would allow us to get rid of just the basic cosine of x's. And so that would be taking the right side, sine of x, times 1 plus cosine of x, and multiply it by its conjugate of 1 minus cosine of x. Okay, that is the most formal. But again, that takes some recognition. And while we've talked about conjugate pairs, we haven't really emphasized them. And I don't know that many of us, me included, is going to look at this and just immediately say, oh, let's multiply by that conjugate. Okay, now, when we multiply by that conjugate, we're going to eventually get like 1 minus cosine squared. Some things will cancel out, and we'll eventually get it to match the right side. I'm going to share a way that is just a little bit more simple for where we are kind of at with these identities. Okay, and that's going to be just working with the equation in general. If we can just get both sides to be the same, that really counts as another way to verify. So what I emphasized yesterday, working with one side independently, we're going to do that 90% of the time. But the 1 out of 10 times, okay, we can actually just try to work with the equation and get them to be something equal, like 5 equals 5 or sine of x equals sine of x. So we're going to do that here. So since I have one fraction equal to another, this is where we can essentially cross multiply. So I take the denominator of this first fraction, multiply it by the numerator of the other, and vice versa. So I'm going to do sine of x times sine of x is sine squared of x, and it equals 1 minus cosine of x times 1 plus cosine of x. So that's more of like a natural way of solving equations and dealing with equations. And again, that would be like a very last resort. And so on this right side, this needs FOILed. So 1 times 1 is 1. 1 times cosine of x is cosine of x. And this is that same conjugate pair that we would have gotten in that more formal way. And so you're going to see that when I do this negative cosine of x times 1, you get negative cosine of x, those cosine of x's will cancel out. Okay? And then negative cosine times positive cosine is negative cosine squared of x. Conjugate pairs is what gets rid of just that regular cosine of x, leaving us with sine squared of x equals 1 minus cosine squared of x. And we saw this yesterday where we have a Pythagorean identity that says sine squared of x plus cosine squared of x equals 1. Well, if we subtract cosine squared of x, I get 1 minus cosine squared of x, which matches up with where that right side is, and that is equal to sine squared of x. So by us getting both sides to be the same, we're technically verifying that identity. Okay, that's really what we're working towards doing, is showing that both sides of these equations are the same. And most of the time, it'll just mean solve one side and manipulate it to get to match the other. And this brings up another point that there's lots of ways to verify these. There's not one clear-cut way. Okay, we could have done the more formal way or this kind of solving method that I used here. Okay, well, I'm going to have you all do the next one. And just like before, that's going to go on the sheet that's going to get turned in. And we'll do like 3 minutes and a little bit extra, okay, before we move on. The thing that I'm noticing here that's different than all the identities we've seen thus far is we're taking sine of negative x. Now, on that identity sheet, the very bottom set of identities that we have not used yet is what's called the even-odd identities. And that is correlated to whether or not the trig functions have even or odd symmetry. We did talk about even or odd symmetry back first semester, but it's been a minute, okay? And again, we don't need to memorize these things. But what I'm noticing here is that sine of negative x is equal to negative sine of x. So that right off the bat is going to be the first thing we're going to take care of. So I'm going to rewrite this left side as tangent of x minus negative sine of x. And then over 1 plus cosine of x. All right, so what I've done is, there we go. Sine of negative x with negative sine of x based on that even-odd identity on your identity sheet. Well, that makes this tangent of x plus sine of x and then over 1 plus cosine of x. Now, once we get here, there's no obvious thing for us to do. Okay, I could take tangent of x and put it over 1 plus cosine of x, sine of x over 1 plus cosine of x. But this 1 plus cosine of x, that's that same kind of binomial term we saw in the last example, where the more formal way to deal with it would be to multiply by its conjugate pair in 1 minus cosine of x. Again, since we haven't really done too much work with those conjugate pairs, I don't know that many of us would say, oh yeah, let's multiply by 1 minus cosine of x. So this will be another case where we'll bring in that right side and let's just work on doing a little bit of solving to get them to be the exact same. And so I'm going to multiply both sides by 1 plus cosine of x to essentially get rid of this fraction and then see where I'm at from there. So when I multiply, the left side becomes tangent of x plus sine of x, and now it equals tangent of x times 1 plus cosine of x. So all I did there was multiply everything by 1 plus cosine of x to get rid of the dividing by 1 plus cosine of x. So now our identity is that tangent of x plus sine of x equals tangent of x plus tangent of x times cosine of x. Well, this looks really close to being the same, right? They each have a tangent of x, but the second term, one is sine of x, the other is tangent of x times cosine of x. And so basically we want to get this tangent of x times cosine of x to somehow equal just sine of x. Well, we have an identity, the quotient identity for tangent, that allows us to write tangent as sine over cosine. So I'm going to work with this right side here and say that tangent is now sine of x divided by cosine of x, and then we're still multiplying by that cosine of x. The left side hasn't changed. And by rewriting tangent as sine over cosine, now the cosines divide out, and so we're left with tangent of x plus sine of x equals tangent of x plus sine of x. And since both sides are the same, we have verified that the starting identity is equivalent to each other. Okay, so even though we didn't end with the left side being just tangent of x, because we get to the same place, we can conclude that tangent of x minus sine of negative x divided by 1 plus cosine of x will always equal just tangent of x. Yeah, Avery, what you got? Let that be a warm-up, that checkpoint 7 when we come in on Thursday, and I'll revisit that. But I want to get you all working. We've already spent more time together as a class than I would have liked. All right, so we've now kind of seen, for the most part, want us to work with identities just one side at a time. We've seen that it might also be beneficial to us to kind of do some solving within the equation. But now we're going to see one where we're going to work with each side independently, more like what we were doing yesterday to try to get these to be the same. So I'm going to start with this left side, and I'm noticing I've got 1 plus cosine of theta and then 1 minus cosine of theta in my denominator. Well, I'm going to multiply both of those by the other denominator to work to get a common denominator. So I'm going to take this 1 over 1 plus cosine of theta, and I'm going to multiply it by 1 minus cosine of theta. 1 minus cosine of theta. I'm going to do the same thing with the 1 divided by 1 minus cosine of theta and multiply it by 1 plus cosine of theta. So far, only working with the left side. So I'm going to have to do some foiling in the denominators. What's nice is they're going to work out to be the same. So once we FOIL it once, it'll FOIL out the exact same way. So 1 minus cosine of theta is this new numerator. The denominator, I get 1 times 1 is 1. I get negative or positive cosine of theta minus cosine of theta. And then negative times a positive makes this negative cosine squared of theta. And then essentially the same thing, 1 plus cosine of theta over that same denominator. And I'm going to do two things here just to, again, save us some work. One, I'm going to cancel out these cosine of thetas. That's a result of us multiplying by that conjugate pair. And I'm going to write this as just one fraction. So I'm going to go ahead and do the addition here and see where this gets us to. So my new numerator is 1 minus cosine of theta plus 1 plus cosine of theta over 1 minus cosine squared of theta. And it looks like in our numerator, we have 1 cosine of theta, or excuse me, a negative cosine of theta and a positive cosine of theta that cancels out, leaving us with 1 plus 1, which is 2 over 1 minus cosine squared of theta. All right, and we're trying to see how can we get this to match up with 2 plus 2 cotangent squared of theta. I'm not seeing anything quite this obvious yet. And so I might actually transition to that right side and see if there might be kind of a hint as to what I want to do with this left side. Well, actually, one thing we could do, we've seen this 1 minus cosine squared of theta show up before. What does that equal? Sine squared of theta, as just rearranging the Pythagorean identity. So let's actually take this, and I'll just keep working on the left side here. Let's take this and write it as 2 over sine squared of theta. And let's pause it there. I am seeing that I can maybe do the reciprocal. Reciprocal of sine is cosecant, so maybe this is 2 cosecant squared of theta. So we might come back and change that here in a second. But now let's look at the right side and see how we might be able to work with that right side and get it closer to where we're at with where this left side is. So what's the first thing you notice about the right side? What do both those terms have? A 2, so let's factor that out. And I get 1 plus cotangent squared of theta. And so I'm wondering if there's a Pythagorean identity that is of the other form of this 1 plus cotangent squared of theta. In fact, not only is it another form, but I see it exactly. 1 plus cotangent squared equals cosecant squared. So this actually equals 2 times cosecant squared of theta. And so I'm like, you know what? These are really close because 1 over sine squared is cosecant squared. So this is actually 2 cosecant squared of theta. And now that I have the left side and right side matching, that is our verification for this identity. So a lot of work on the left side, just a little bit of work on the right side. And lots of algebra again. Okay, let's skip the you try the problem because I have plenty of practice for you all on your actual assignment. So let me just out with one just kind of summary of all these identities. And then another thing that I will suggest for you all before we're all done. Okay, so we'll skip that. Like I've kind of mentioned, there is often more than one correct way to solve a puzzle and thus to verify these identities. I touched on that as we went through this today and even yesterday. One method might be shorter and more efficient than the other, but find a way that works. Okay, the more identities that you do, the better you're going to be. And that's why I kind of set up class this way, because we just need to practice them. Okay, so right here, and I'll leave this up on the board for anybody that wants to, if you want to add this in your notes, fine, but this is just kind of a summary as to how can we attack these identities? How can we get started with them? And what are some steps we can do to ultimately prove these identities? Okay, so read through this as you're working on the homework. Refer to this. I'll leave it up on the board. If you want to add it into your notes, add it into your notes. The very last thing that I'll say,